Yeah, sorry. Okay, so let us start. So semaphores, monitors, and message passing, these are the widely used methods for achieving mutual exclusion and synchronization between multiple processes. And so then what is semaphore? So semaphore, we can think of it as a kind of token or lock which is used by multiple processes to enter in the same critical section. So whichever process has that particular lock or that token, that process can enter into the critical section. Other needs to wait. But when we talk about implementation of this semaphore, basically it is an integer value and it is used to signaling among processes. And there are only 3 operations which can be performed on a semaphore. And all these operations, they are atomic operation. It means whenever this operation, one of the operation is being performed, no one can interrupt that. So this atomic operation, which can be performed on semaphore, are initialized. You can initialize some value to this semaphore. Then you can decrement this semaphore value using some operation called semWait, and increment using the operation called semSignal. So these are the primitives actually. Primitive operations that you can perform on any semaphore. So let us try to understand how this semaphore gets implemented. If we use some C kind of programming structure, how this semaphore can be implemented. So you can see this is one kind of structure, we call it semaphore. Okay, and it contains 2 things, count and the queue. Now why, what is the purpose of this queue? Count is like integer variable, right? So we understand that semaphore is an integer value. Then what is the purpose of this queue? So we'll see. SemWait, basically whenever any process wants to enter into the critical section, it needs to get that semaphore, it needs to lock that semaphore, and for that it needs to call semWait. If it is allowed, then semWait will not be blocked. It is not going to block the process and process will enter into the critical section. But if it is, if some other process is already executing in that critical section, and if any other process is calling semWait, then that process will be blocked. So how it is happening? So you can see that semWait is called on semaphore S. Internally, first it will decrement the count of S. Okay, it will decrement this count. And if this count is less than 0, if it is less than 0, then what happens? That means the process which has called semWait, it cannot proceed further. It cannot go into the critical section because someone is already there. So it has to wait. Okay, so in that case, place this process which has called semWait, place that process in the queue. This is kind of waiting queue. Okay, and this process will be blocked. So that's why this queue is used to maintain those processes. This queue is used to maintain those processes which are blocked on particular semaphore. And semSignal is opposite to that. semSignal, what it will do, whenever any process completes its critical section, now it needs to release the lock. It needs to release the lock. So to release the lock, it will call semSignal. And when it calls semSignal, first of all, the count will be incremented. And then after incrementing the count, it checks. If still count is less than or equal to 0, it means there are some processes which are waiting on this semaphore. When I was executing critical section, at that time some processes came to you which are waiting now for this semaphore to be released. So what should I do as a releasing process? The process that is releasing the semaphore, what it needs to do, it will increment the count and check the count number. If count is still less than or equal to 0, it means some process is still waiting. So remove one process P from this queue, because this queue contains those processes which are waiting for the semaphore. So remove one process from that and place that process P in the ready list or on the ready queue. Okay. Are you getting this idea of semaphore? Yes, are you getting the idea? see, you need to be very much clear with this semaphore idea. Otherwise, you won't understand the further concept that we are going to discuss today. This is the most important, you can say, widely used concept for mutual exclusion, semaphore. Though concept is very simple, but when you use it, until unless you are very much clear, you cannot use it properly. There are very high chances that you can make some mistake. So please let me know if you are still having any doubt. Okay, in that case, let me ask you one question. As I told you, there can be three operations: initialize, decrement, and so decrement and increment. Decrement operation performs inside same weight. Increment operation is performed same thing. What do you mean by initialize? So what is going to be initialized? When I say semaphore is initialized, what will you be? What is going to be initialized? Yeah, can anyone tell me what will be initialized when semaphore gets initialized? Because semaphore here, it is a structure kind of stuff which contains count and queue. Yes, anyone? Okay, someone says count equal to 0, queue equal to none. Okay, let us say count equal to 0. Okay, suppose count is initialized with 0, and let's say there are two processes. Out of this, one is trying to enter into the critical section. So whenever any process tries to enter into the critical section, first it needs to call sem. First it needs to call which primitive or which operation it needs to perform. When any process wants to access critical section, same weight, yes, same weight. So let's go there. Let's say P1 is trying to access same weight. I mean, it is trying to call same weight. Count is initialized with 0. So what will be the value of count? No, not, yeah, it will be -1, right? Count will become -1. And then it will check if s dot count is less than 0. Will this be true? Yes. If this is true, what will happen to that process which has called same weight? What will happen to it? Will be blocked. So this is the only process which is trying to access critical section. What do you think? Should it be allowed to enter into the critical section, or it should be blocked? What do you think? What should be allowed? Should it be blocked, or it should be allowed to enter into the critical section if it is the only process right now? It should be allowed, right? But if you initialize your semaphore with 0, it won't be allowed, right? So basically this count, you need to understand what this count represent. This count represent the number of processes which can enter into the critical section, or which can use shared resources at the same time. How many processes can use some resources at the same time? That is the initial value of this count. Now, if we are talking about the critical section, okay, where you may be going to, change some data. So maybe, okay, tell me how many processes you would allow to execute that particular critical section at a time. How many processes you would allow? If there is a critical section inside which some data is going to be changed by different, whoever is executing that, it is going to change the data. So at a time, tell me how many processes you would allow to enter into the critical section. Only one, right? So now tell me what should be the initial value of this count? 1, exactly. It should be 1, right? It should be 1. So normally initial value, you can either have some value 1 or more than 1. Now more than 1, does that make sense? If I initialize this count value which is greater than 1, does that make sense? Let's say I am initializing it with 3. How many processes can enter into the critical section at the same time? if I initialize it with 3, at a time, how many processes can be there inside critical section? Is it that difficult? Is it that difficult to understand? No one is answering. Why only 1? If count is 3, how many processes can call same wait without getting blocked? How many processes can call same wait without getting blocked? Because blocking occurs only when same count, this count becomes negative. First, no, 3 processes. Why 4? First process will make it 2, second process will make it 1, and third process will make it 0. So 3 processes will be allowed in the critical section. But if 3 processes can simultaneously execute critical section, should it be allowed first of all? No. But see, it depends. What kind of resources are being shared, it depends on that. For an example, let's say the resource is printer and you have 3 printers. You have 3 printers. So how many processes can print at the same time? 3. So what is the purpose of this semaphore that you are using, or what kind of resources it is trying to protect? It depends on that. If you have multiple copies, or like this multiple, let's say multiple printers you have. So in that case, you may allow those many processes to execute simultaneously. Okay, and in that case, you allow, if you use semaphore to protect that printer resource by getting corrupted by different processes, at a time you allow 3 processes. So in that case, count will be initialized with 3. But if the semaphore is being used to protect some code which is changing a single copy of some data which is being shared, in that case you would allow only 1 process to execute in the critical section. So this count, initial value of this count depends on what kind of resources you are protecting with the help of semaphore, and you are trying to achieve mutual exclusion. So it depends on that. But generally, in general design, this initializing or the initial value of this semaphore is greater than or equal to 1. It is greater than or equal to 1. Now, can anyone tell me, let's say count is 1, initialized with 1. First process calls same wait. So it will reduce it to 0. It will decrement it to 0. But it is not less than 0. So it will not be blocked and it will allow to enter into the critical section. So while P1 is, let's say, executing in the critical section, some other process comes. Let's say some other process comes. Okay. Now, if that process tries to call same wait so that it can enter into the critical section, what will happen to this count value? What will be the value? Yes, -1, right? It will be -1. And if it is -1, then it will be block. So P2 is, let's say, block. P1 is executing, P2 is block, P3 comes, and it is also calling same wait on the same semaphore to access the critical section. What will be the value of count now? -2. And it will also be blocked. Yes, it will also be blocked. So tell me the negative value of this count, whatever the value is there of this count, negative value, what does it denote? The negative value, whatever negative value is there, exactly number of block processes. So that denote number of block processes. And positive value, it denotes how many processes can enter into the critical section, or how many processes can share the resources simultaneously. That is denoted by the positive value of this count, and negative value of this count represent or denote how many processes are blocked on this particular semaphore. Does this make sense? Are you getting? Yes. So now, if we restrict this definition of semaphore by putting a constraint that semaphore value, this count value, can either be 1 or 0. It can be 1 or 0. Only these two values are possible. It cannot go beyond 1. That is, it cannot be 2, 3, 4. It cannot be minus value. So it can be 1 or it can be 0. And that kind of semaphore is called binary semaphore. That kind of semaphore is called binary semaphore. And you can see this implementation. This kind of design can be there. Binary semaphore has now some value which can either be 0 or 1. Are you aware of this enum enumeration? Have you used this enum data structure or data types rather? Okay, so the enum means whatever values you provide, only those values can be given to this variable. So this value can be either 0 or 1, and then there is a queue. And now instead of same weight, we call it same weight B, just to denote that this is for binary semaphore. B for binary semaphore. So same weight B, what we do? First of all, we check the value of, we check this value. If this value equal to 1, it means this process can enter into the critical section. So first it will make it 0. First it will make it 0. Else, if it is not 1, it can be 0, because this is binary semaphore. So it can be 1 or 0. So if it is not 1, then this process has to wait. It will be blocked and it will be put into the queue. So it is not going to decrement it, right? It is not going to decrement, but it just, you can say, toggle the value. I hope you remember compare and swap or exchange, where we actually did the same thing. We toggle the values, especially in exchange, 1, 0. Similar to that, this semaphore behaves. It will check the value of this value. If it is 1, it will make it 0. If it is not 1, if it means it is already 0, it means some process is already executing in this critical section. So I cannot enter. So I need to wait. Similarly, there is same signal B, which is going to be called after executing the critical section. Process wants to release the semaphore. So it will call same signal B. And at that time, now it will check one thing. If s.q is empty, then only make this value 1. Otherwise, don't make this value 1. Okay. Otherwise, what you need to do, if this s.q is not empty, it means there are some processes waiting for on this semaphore, then don't make this value 1. Then don't make this value 1. Rather, remove a process from that queue. One of the process will be removed and it will be put into the ready list. It will be put into the ready list. So can you tell me now, by looking at this definition, can you tell me how many processes can be blocked on same semaphore? Because there is no negative values which represent the number of block processes. But can you tell me how many processes can be blocked on this kind of binary semaphore? Exactly that is what we are discussing. If count is 1 and same weight is called, but process is terminated before calling same signal, yeah, that is a different case. That we will see. Okay. Okay. So someone is saying 0, someone is saying 1. Let us take example. P1 comes. Currently, this value is 1. Suppose this value is initialized with 1 value. And someone calls same weight B. What will happen? Will it be blocked or it will be allowed? Allowed. Because in that case, this value will become 0. That's it. But then it will be allowed. There is no blocking. So process P1 is allowed, but it has marked this value 0. P2 comes, then now what will happen? P2 comes. It will check this value. Is it 1? S dot value, is it 1 when P2 comes? No. So it will be blocked. So it will be blocked. Okay. P3 comes, then now P3 comes. While P1 is executing in critical section, P2 is blocked. P3 will also be blocked. P4 comes, it will also be blocked. So there is no restriction on how many processes can be blocked on same semaphore, same binary semaphore, right? Because we are not limiting until and unless this queue is full. That can be limitation. The queue size can be the limitation. If any limitation is there, it is nothing but the queue size, how many block processes it can contain. But generally this queue, it is not limited, right? Until unless OS provides some limitation. Okay. So even though this is binary semaphore, how many processes can be blocked? There is no limit on it. Any number of processes can be blocked. Okay. Now, let's say there are 4 processes which are blocked. And the process P1, which was executing in critical section by locking this semaphore, now it is going to release it by calling sem signal B. So what will happen? What will happen? What value, what would be the value of this value variable when sem signal B is called by P1 now? Still it remains 0, right? Because S dot Q is empty. No, it is not empty because 4 processes are waiting. So this is not empty. So don't change this value. It will simply remove one process and allow it to execute. Again, that process which completed, that process which completed, it will call sem signal B. Still Q is not empty. So basically Q, this value will become 1 when there is no blocking process on this. There is no waiting process on this semaphore. Then only it will become 1. Are you getting the working of this? Okay. So now there are 2 types of semaphore: weak semaphores and strong semaphore. Actually, there is nothing much different. Okay, let me ask you one thing. The blocking processes which are put inside this queue, and whenever there is a signal, one process will be removed. Which one process should be removed? Because it says remove a process P from S dot Q. It is not mentioning which process. So what do you think? Which process should be removed? Normally, that is how we think about queue, right? It is FIFO, first in, first out. So whichever process entered in that queue first, that should come first, right? That should come out first. That is FIFO order. And if this FIFO order is followed, then it is called strong semaphore. While unblocking some process on particular semaphore, at that time, if this queue order or FIFO order gets followed, then it is called strong semaphore. If it is random or if there is no such order, then it is called weak semaphore. That's it. See, it is also possible to implement this removal of the process from S dot Q. Okay, you can think about this queue as an array, just an array, and you can remove any random process from that array. And if that is the implementation, then it is weak implementation of semaphore. But if you follow the order, first in, first out, then it is strong semaphore. Then it is strong semaphore. Are you getting this? But most of the time we work with strong semaphore because that is how it should be. It should not be random, right? It should be ordered. And that's why most of the time we work with strong semaphore. But this is for your knowledge that this kind of implementation is also possible. Okay, someone is asking, can we use here a variant of queue? Like, yes, that is possible. That is possible. This queue can have any order. It can be priority queue also. Correct? So let us see one example of strong semaphore mechanism, how it behaves. So for that, you need to understand here what is the case. This process A, B, and D, process A, B, and C. These three processes, they are waiting for some result from process D. So whatever D is generating, that is being weighted by A, B, and C. Okay, that is the example here. Process A, B, and C, they are waiting some result from process D. So it means that A, B, and C, when they call same weight, okay, it will be released only by D by calling same signal. So D is the only process which calls same signal. A, B, and C, they are actually calling same weight. Are you getting this setup of this example? What is the example? A, B, and C are the processes which are calling same weight, and corresponding signal will come only from one process, that is D process. So let us understand this example. Initially semaphore is 1. Initially it is 1. This is blocking queue for semaphore. These are the ready queue for processes. Okay. Now a process comes and gets the processor and gets executed. So it will call same weight on this S. So what value will be there? What A will do with this value S? When A calls same weight on this S, what would be the next value of this S? 0. And A will be blocked. A will be blocked or not? Will it be blocked or not? No, because S is not less than 0. If S is less than 0, then only it will be blocked. It means some result is already available. You can think that way. So A will make this 0 and execute in the critical section. And after doing something, it will join which queue? This queue or this queue? After completing its job, or after completing its time quantum, where it will join this process A. Let's say it is not completed. Process is not completed. It will definitely join ready queue, right? So this is the case, right? This is the case. A will join here ready queue. Now B comes to the processor and it is going to execute. But as at this time S equal to 0 and B calls same weight. What will happen to this B? What will happen to this B? Okay, what value will be there for S? When B calls same weight, what would be the next value of S? Let's consider this is our counting semaphore. Okay, this is our counting semaphore. Okay, I forgot to tell you, binary semaphore can take value 0 or 1 only, and the other general semaphore, that is also called general semaphore or counting semaphore. That is the another name. The basic, this semaphore primitives that we discuss, where value can be positive or negative, that is called counting semaphore or general semaphore. That is the name. And otherwise you have another type of semaphore, binary semaphore, which can take only 0 and 1. So now here, let's come back here. So what value will be there for S? -1 when B will call same weight. And where B will join? Will it be allowed to enter into the critical section? Or will it be allowed to access resource for which it is waiting? No. So where it will join? It will be blocked. B will be blocked on calling same weight. S will become -1 and B will join here. So B will join here. Okay. And S is -1. Now it is turn for C. No, sorry, it is the D's turn. It is D's turn. And D is the process which calls same signal. D is the process which calls same signal. So what is the next case? What value will be there for S? It will become 0. Yes. it will become 0. And then where D will be joining? This queue or this queue? D will be joining which queue? Ready queue or block queue? Yes. Would you like to answer? Are you getting? D, which calls SEM signal, which makes this S equal to 0, then it is never going to block because it is not calling SEM wait. So it is not going to join here until unless, okay, see, you need to understand this is the block queue for semaphore. This is not block queue for any other event. D may be block on some other event, but that is not that is not the case that we are taking right now. We are taking only blocking on semaphore. But D is not blocking on semaphore, so definitely it will join here in ready queue. So this is the case. D will join here actually. It will make it 0. I forgot to show it here, I guess. Yeah, I forgot to show that, right? Here I forgot to show. No, that's fine, right? Okay, so it is going to make it 0. Now, interesting thing is when D will make it 0, D will make it 0. At the same time, it is also going to unblock this process because this process was waiting on semaphore. So whenever there is a signal, at least one waiting process, not at least, actually exactly one waiting process will be removed from block queue and put it into the ready queue. So D, when it calls SEM signal, S will become 0. This block process will go into the ready queue, and then after D will join here ready queue. So you can see D is joining after B. D is joining after B. But this order can be changed, okay? It depends on OS, how it behaves. But mostly, first D calls SEM signal, and as soon as it calls SEM signal, B will be unblocked and put it here. And then say C comes next. Currently S is 0. Currently S is 0 and C is calling SEM wait. What will happen to C? What will happen to C if it calls SEM wait? Again, it will be blocked, right? And this is the final, actually, it is showing that C makes it -1 and joins here. A execute, makes it -2 and joins here. B executes and makes it -3 and joins here. So this is the last case that it is showing. And when D will execute, now after this D will execute, what will be the value of S? So there are some steps which are ignored or which are clubbed here. Few steps are clubbed here. So now when D executes, what it will make to this? -2. And what will happen to this two queues, ready queue and block queue? What are the processes in this queues? C will go inside ready queue and BA will remain in block queue. Are you getting this? Everyone, are you getting this? This is very important concept that you need to understand. Now let us see how this this semaphore can be used to achieve mutual exclusion. Okay, how this semaphore can be used to achieve mutual exclusion, that is what we are going to see. So very simple code is there, because now you just need to call SEM wait and SEM signal before critical section and after critical section. That's it. This is the simplest case. There are n processes which are started by main function, you can say that way, and each process wants to execute some same critical section, let's say, okay, same code. So each process will execute this code, but before entering into the critical section, it will say SEM wait S, and S is initialized with 1. Here we see this semaphore S as just an integer. Okay, we see that as an integer only. Internally, it may be a structure like, We don't know how it is implemented. That was just the idea. What we discuss here, this is just an idea. Okay, this is just an idea. But when we actually use this semaphore library that we have in C, maybe if time is permitting today, I will show you. Okay, we treat this semaphore as just an integer. So we initialize it with 1. We are not saying s dot count equal to 1. Okay, we just initialize it with 1. It means only one process can enter into the critical section at the same time. If other process tries, it will be blocked here. It will be blocked here. And whenever any process completes this critical section, it will signal it. It will signal it. So it will release that lock. Are you getting? So if you compare this approach, this semaphore approach with those software approaches that we discussed, Decker's algorithm, Peterson's algorithm, do you find that this is easy to use rather than those algorithms? Do you think so? Internally, it is doing the same thing. But for us as a programmer, now it is simple. We just need to call this SAMWait and SAMSignal. Right? Definitely, structure seems less complex. But internal behavior may be the same thing, right? It is not changing. But as a programmer, we are definitely more comfortable with this less complex structure. Why we require this less complex structure? Because when we deal with some complex examples like producer consumer, where we have two things to be achieved, one is mutual exclusion, another is synchronization, and we are going to achieve mutual exclusion plus synchronization at the same time using different semaphores. At that time, we just need to call SAMWait, SAMSignal on different semaphores and we are sorted. Of course, we need to make sure that we are doing it in a correct order. Order is very important. Order of calling SAMWait as and SAMSignal as is very important. There is another concept called mutex. Mutex is nothing but binary semaphore. You might have heard this mutex. Mutex is short form for mutual exclusion. But that construct, mutex construct, is same as binary semaphore. The only difference is binary semaphore. Okay, in binary semaphore, it is possible that one process called wait on that and another process called signal on that. That is possible. But mutex is the construct where the process which calls wait, only that process can call signal on that. And then after another process, wait and signal pair on mutex is there, must be there in the same process. Whereas in binary semaphore, there is no such restriction. P1 can call SAMWait and corresponding SAMSignal may come from P2. That is possible in binary semaphore. But if you use special type of binary semaphore, which is called mutex, this is the difference. So you need to know this difference, mutex and binary semaphore. Otherwise, they are same. So let us understand this. If there are three processes A, B, and C, okay, how they will behave. So you can see this dark arrow is critical region. This normal arrow is normal execution. That is another code than the critical section. And this dotted arrow is a block state. Blocked on semaphore. That is a lock. So you can see that this is the queue for semaphore lock. This is the blocking queue for semaphore. And this is value of semaphore. So initially semaphore value is 1. A is the first process which calls SAMWait on that lock. Lock is the name of the semaphore. Instead of S, they are using another name, lock. So it's a variable. So SAMWait lock. A is the first process which calls SAMWait lock. So in that case, it will change this value from 1 to 0. It will change this value from 1 to 0, and it is the only process because this is 0. So it can start executing in critical region. It can start executing critical section. Okay. Meanwhile, it is executing in critical section. Of course, B has already started. And at this point, B also wants to enter into the critical section. And it also calls same weight lock. But then lock value is 0. It will become -1. And this process B will be blocked. This process B will be blocked. And it will be put here. So you can see B is blocked. When A is executing critical section, B is blocked, C is also executing, and at this point it also wants to enter into the critical section. But as lock is -1, it will make it -2 and it will be also blocked. It will also be blocked. Now when this A completes critical section, it will call SEM signal on that lock. So it will make this -2 into -1. But as it is incrementing, it will release, it will get one process out of this queue and put it into the ready state. So B will become ready. And you can see now B enters into the critical section. B enters into the critical, and B completes its critical section at this point, and it calls SAM signal on that lock. So it will make this -1 to 0, and C will be released from this block queue and go into the ready queue, and it can enter into the critical section. And then here they are normally executing. They are executing some normal code, which is not critical. So they can be in parallel. Normal code execution can be in parallel. Only critical section code execution is sequential. Are you getting this example? Yes, are you getting this? So now we are going to discuss one classical problem, producer consumer problem, where we need to achieve mutual exclusion as well as synchronization between two different processes, producer process and consumer process. Okay. And for that, we will see how we can use Semaphore to solve this problem. But before we solve this problem, we need to understand the problem. What is producer consumer problem? So, general situation. You think that you consider that one or more producers are generating some data and placing those data in some buffer. Producer is one process. There can be one or more producers which are producing some data and put that data in the same buffer. Okay, buffer is common between all producers. There is a shared buffer among all these producer processes, and whoever generates data, that process puts that data inside the same buffer. There is another process called consumer. A single consumer is there who is consuming that produce item from the same buffer one at a time. And the limitation is, as this buffer is shared by multiple producers and consumer, these are the different processes which are sharing the same resource. So only it needs to make sure that only one producer or consumer may access the buffer at any one time. At any particular time, only one process must be accessing that buffer. If it is producer, maybe it is putting some item. If it is consumer, maybe it is getting some item. So what is the constraint? Ensure that the producer can't add data. Okay, there are some other constraints. This is one thing, that at a time only one process should access that buffer. Okay, that can be considered. As well as another constraint is ensure that the producer can't add data into full buffer. If buffer is full, producer can't put any more data, and consumer can't remove data from empty buffer. So that producer and consumer need to take care of. Let me know whether you are getting this problem statement or not. What is producer consumer? Or if you can visualize this kind of problem that you might have seen in real world or even in computers. Have you ever seen this kind of producer consumer situation? If you can think of it. Can anyone give me example where you can have seen this kind of situation, that there is a single buffer Multiple producers can produce some item and put it into the single buffer. Consumer is single consumer, which is consuming one item at a time from that buffer. But at a time, only one can access that buffer. Yes, you can say database on server, correct? But then who is the consumer? Any process which wants to read that data. Can we say that? And producer who is putting some data, right? So that is fine. Database can be considered for this. So database is your buffer, you can say. Database is your buffer, where some processes generate some data and put it inside that, and consumer may consume that data, right? Another simple example is at low level, when clients send requests to any server, there can be multiple clients who are sending requests to same server. So server is consumer, because the request that you send, those requests will be put in some buffer at kernel level. If you really learn this client server architecture and how they behave at kernel level, have you gone through this network subject? Have you gone through this network subject? Anyone? Okay. So normally what happens, client server architecture, whenever request comes to the server from different customers or different clients, they all put into the single buffer, from where server will read one request at a time and entertain that request, maybe through different other processes or other threads. So that is another example. But this is a very general situation which can occur in different cases. Which can occur in different cases. Okay. So let us say, assume that the buffer, right now we assume that buffer is infinite. So this constraint will be nullified. I mean, you need not to worry about this. That ensure that producer can't add data into the full buffer. So we start solving this problem with simplifying these assumptions, with simplifying this constraint, with making this constraint little easy. Okay, and then we will solve it for the proper constraint producer consumer problem, right? So let us start with simple situation where you have infinite buffer. Just assume that you have infinite buffer. So producer need not to worry whether I can produce data and put it into the buffer or not. Producer can always produce data and put it into the buffer, because it has assumed that there is infinite buffer. Does that make this constraint does that nullify this constraint also? If I use infinite buffer, the consumer constraint, is it nullified or it is still there? What do you think? If I use infinite buffer, consumer constraint that it can't remove data from empty buffer, is it still there or it is also nullified? Anyone? Are you there? See, forget about that. Yeah. So constraint is still there. Constraint will remain there. Whether producer is producing first or constraint will remain there, that it cannot remove data from empty buffer. How can it remove any data from empty buffer? So this constraint will remain there whether buffer is infinite or not. Okay. So only constraint that is eased out is this, that producer need not to worry. Now this format is little bit disturbed, but still you can read it. Consider this B as buffer. B is your infinite buffer, which is nothing but one array of elements, linear array of elements. Okay. So normally what producer does, producer continuously producing item. So it has one infinite loop. It will produce item V and put that item V in this buffer, where in is one index of that that array. In is the index for producer, and it will increment that index to put the new item. Similarly, consumer is also infinite loop, but what it checks, it has its own index out. Both in and out are initialized with 0. Both are initialized with 0 or -1, whatever you call it. Because in C, array starts with 0 and 0 is a valid index. So in that case, we can see that in and out both are initialized with -1. Fine. But here before, no, it should be initialized with 0 actually. It should be initialized with 0 because in the first index itself, item is being put. So both are initialized with 0. And whenever producer produces the item, it will say B of 0 equal to V. It will put that item into that buffer and then increment into 1. Now what consumer needs to check, as it cannot consume empty buffer or it cannot consume stale items, it needs to check if in is less than or equal to out, it cannot consume item. It means in must be greater than out. Are you getting this condition? Why it is checking this? Consumer cannot consume empty buffer, or it cannot consume stale items which is already consumed. Cannot be consumed again. So if in is less than or equal to out, consumer can't consume anything. But if it is not less than or equal to out, it means in is greater than out, then consumer will get that item B of out, put it in some variable W and increment out plus plus. This is called consuming item W. Are you getting this? Are you getting this simple producer consumer idea? Okay. So now we need to convert this producer consumer. We need to write this producer consumer such a way that there is no problem of no problem of race condition, and there should be some proper synchronization. So you can think this way. Okay. Currently, producer has produced, lastly it has produced this item. You can think that way because in is pointing here. So it is producing this item. Sorry, this is the new in index where newly produced item will be put. This blue boxes means items are produced. These items are already there. This is empty boxes. If consumer has consumed some item, then that is going to be empty. Or producer has not produced items, so still it is. So in is right now pointing here. So whatever new item will be produced by the producer, it will be put here, and then in will be incremented. Similarly, out is going to consume this item, and then it will be incremented to this. So this is how it is working, and it is infinite buffer. And you can see if in is greater than out, then only consumer can consume the item. I hope this will help you to visualize. Okay. So what is some possible solution of this problem? Because we need to achieve mutual exclusion, as there is a shared resource buffer. There is a shared resource buffer, and there is some value n which represent how many items are there which consumer can consume. N represent, basically n is nothing but in minus out. N is nothing but in minus out. 4 minus 1, that is 3. So there are 3 items which can be consumed. Are you getting this? N represent how many items are there which can be consumed, and N is nothing but in minus out. In minus out, that is 4 minus 1. So it represents there are 3 items which can be consumed. Okay. So let us try to understand this. Main function will initialize n equal to 0 because initially there is no item to be consumed, and then it starts producer and consumer. See, then it starts producer and consumer. Now this is the producer and this is the consumer. So producer process will execute this code, consumer process will execute this code. There is one binary semaphore S which is initialized with 1, and there is one delay equal to 0. What is the purpose of delay? We'll see. And n is representing number of items which can be consumed, right? So let us try to understand. And again, both are infinite loop, but producer, what it does, producer, as it is infinite buffer, it need not to bother whether I can produce item or not. It simply produce. It simply produce the item. And then it will call same weight B on S, because now it needs to put that item into the buffer. Item is produced, but now that item needs to be put into the shared resource buffer. So the code which execute or which accesses some shared resource, that is our critical section. And before entering into the critical section, you should call same weight. So it is calling same weight B because it's a binary semaphore. If it is permitted, let's say it is permitted because initially there is one value, so it will be allowed. So what it will do, it will put that item inside the buffer. Append is the function which will put that item into the buffer. Okay, so we assume that append will put the item into the buffer, and it will say that number of consumable item is increased by 1. It does not know what is current value of n. It does not know. It simply increment that because it has produced one item, and it will tell that one more item is produced, so it will increment n. But at the same time, it also do this. What it does, if n equal to 1, so after incrementing n, it will check, is it the first item which is produced? If it is the first item which is produced, that it needs to tell the consumer that you can start consuming. It needs to tell the consumer that you need to start consuming by signaling delay. So this is for synchronization. This is delay is the semaphore which is used for synchronization, and initially it is 0. Initially it is 0. Now here there are two semaphore. S is the semaphore for mutual exclusion, and delay is the semaphore which is used for synchronization. What kind of synchronization? What kind of synchronization? Can anyone tell me? What kind of synchronization is being performed between producer and consumer? Yes, anyone understands this? You can see consumer, what it does. It says same weight B delay. Before doing anything, it says same weight B delay. Initially delay is 0. Let's say initially delay is 0, and consumer is the first process. Just assume that consumer is the first process which gets executed before producer. Suppose, can consumer consume? Before producer, consumer gets executed first because we don't know the order. Order can be anything. Can consumer consume if it is executed before producer? No, it is not possible because buffer is empty. Buffer is empty, correct? So buffer is empty, it cannot produce. So what it is waiting for? Initially delay is 0. You can see initially delay is 0. And when consumer calls same weight B delay, it means it is waiting for producer signal. It is waiting for producer signal that I have produced some item and you can consume. So this delay is for that. Before starting consuming, it needs to wait for some data to be there to be consumed. So that's why if consumer executes first, delay initially 0. So this will be blocking the consumer. And of course, when it will be blocked, producer will get a next chance. It will produce some item, and if n becomes 1, which is initially 0, initially it is 0, right? So first item when it is produced, producer checks if n equal to 1, yes, this is the first item. So I need to tell the consumer that now you can start consuming. So it will signal that delay. As soon as this will signal the delay, now consumer will be unblocked. Consumer will be unblocked. Are you getting? So this is the example of binary semaphore where wait on delay is called in one process, wait on some semaphore is called in one process, and signal is called in another process. But this is not possible with mutex, which is also binary semaphore. But mutex is a special binary semaphore where whoever calls wait on that same process signals that, like this S, like this S. S is here, you can consider it as mutex. But this S is used for mutual exclusion. That's why it is called mutex. And delay is used for synchronization. Delay is used for synchronization between producer and consumer. Producer says, okay, you consume. Producer says, okay, you can consume. Like that. and then it will complete its critical section by signaling S. And consumer, as I told you, it will first wait for delay. If item is there, then delay will be unblocked. So consumer will be unblocked, and then it starts consuming. But before start consuming, which is being where consumer needs to consume from this shared buffer, it needs to call this lock. It needs to acquire this lock on S. So again, it will say same wait B S. If it is allowed, then it will take the item, reduce the n value because it has consumed 1, so n minus minus, and then it will signal S that okay, I have consumed, so I will release this critical section. And then it will consume because this is local process, I mean local function. It also checks that, it also, because it needs to wait again, if it has consumed the item and there is no more item left, no new item left to be consumed, it will check if n equal to 0, I need to wait till producer signals. Till producer signals, I need to wait. Does this make sense to you? Everyone, does this make sense to you, or any question up to this point? So these are very complex things unless you understand it properly. Okay. So if you don't understand it properly, then you are not going to get the following things. Okay. Can anyone tell me, is this the complete solution? Is this the correct and complete solution, or you can see any problem there? So it is not that easy to visualize the problems in such, such programs, but this is actually incorrect. This is incorrect solution. Why? Because there can be a situation like this. Okay, let us understand. Suppose producer is the first process. Suppose, again, this is very specific scenario we are taking, because if we try to justify this code, okay, if we want to prove that this code is correct, it should cover all possible cases, and in all possible cases it should behave properly. If that is the case, then only this code is correct. But we have one particular case. This is only one particular scenario. Okay, there can be more than one such scenarios where problem can be there. So let us understand one particular scenario. What happens if producer executes first? Let's say producer executes at this point and it calls same wait B on S. So S will become 0, n is still 0, delay is 0. Initially, these are the values. These are the initial values. But as soon as same wait B is called, S will become 0, n is still 0, delay is still 0. Are you getting this? Yes, are you getting this? Then what n does? What producer does after getting S? Because S was 1, it has become 0, so it is allowed. So producer is allowed. So it will produce item, and see, some of the steps are ignored here, right? Like append and all these steps are ignored. Okay, append is ignored, produce is ignored, because we are focusing on main part. So after appending, it will say n plus plus. It is going to do n plus plus. So n will become 1. And it checks if n equal to 1, it will signal delay. So as it will signal delay, delay will also become 1. So this is the current position. S is 0, n is 1, delay is 1. And as soon as it will call same signal S will also be 1. So this is current scenario. After this, now consumer starts. Let's say consumer is waiting on delay, but delay is set. Delay is set by producer. So it will be allowed to enter because there is no blocking on delay. It will become 0, but there is no blocking. Then it will call wait on S. If you see this code, consumer, after completing or after clearing this stage, it will enter here and it will block on S. But S is also 1. S is also 1. So it will become 0 and it is allowed to enter into the critical section. And now inside critical section, after taking the item and all those, it is going to reduce the number of consumable items, that is minus minus. So this is 0, this is 0 and this is 0. All these three will become 0. But then after that, it is saying same signal BS. So S will become 1. Now here is the problem. After saying same signal B, so S will become 1, N is 0, D is 0. Okay, both are 0. N and D both are 0, but S will become 1. And let's say before it consumes and checks this N value, before it does that, process gets switched. Let's say process gets switched and producer comes into the picture and it is going to produce new item. So that is one scenario. So it is going to wait on S, but S is already 1, so it will be 0 and it is allowed. S was 1, so it is 0 and it will be allowed. It will say N plus plus. So N will become 1. N will become 1. If N equal to 1, yes, N equal to 1. So it will say same signal delay. So delay will also become 1. And then it will say same signal BS. So again, all these three are 1. Again, all these three are 1. Now, consumer gets resumed and it will resume from this point. So it will consume the item and now it is checking this. Now it is checking this, which it should check before actually. But as it was switched in between, now it is checking N equal to 0. But is N equal to 0? No, it is not 0. So it is not going to wait for delay. This is not going to happen. This is not going to happen. And it will directly enter into the same weight B. Fine. This is up to this point, it is fine. S will become 0. N and D both are 1. It will reduce N. So N will become 0. Okay. It will signal S. So S will become 1. Now it will check N equal to 0. Then it will wait on delay. So N is actually 0. So delay will be, it is 1. So it is becoming 0, but it is not blocking. Actually, N has become 0, but it is not getting blocked. It is not getting blocked because in between, producer has signal delay. Before this was executed for this, in between producer executed and it has set delay equal to 1. And that is why when this time it will check delay, okay, it is still becoming 0. So there is no problem. There is no problem. Are you getting? Yes or no? So as there is no blocking, again it will get into the next stage, same weight B. It will become 0. So it is allowed, but it say N minus 1, N minus minus, and N was 0. So it will become minus 1. This is not proper. N can never go minus. N should not go minus. Okay. It cannot consume item which is not there. Because what is it is doing? It is trying to consume N item which is not there. Because N is already 0. So it cannot consume the item and make it minus 1. So this is some incorrect solution. This solution is incorrect. This solution is incorrect. Especially in that particular case that we discuss. If that happens, if that execution happens, this code, it will crash. And it won't achieve proper mutual exclusion or synchronization. Are you getting this example? Are you getting this example? Okay. So what can be the solution? What can be the solution? Can we do some changes here and can we solve that? Like here, this N checking is inside this same weight BS and same signal. Basically, it is part of critical section, right? Can we put this also inside critical section? Can it be can it be the solution? If we put this checking inside this critical section, can it become a solution? What do you think? Okay, so I'm leaving this question I am stopping this session with that question in your mind, that if I put this part inside my critical section, will that solve this problem or not? With that question, I leave you. And in the next lecture on Monday, we will continue this discussion. So whoever has not joined today, okay, I am not sure whether they will get the further topics or not, and they are actually going to fumble. You can say they are not going to understand anything in next 2-3 lectures. So if they are your friends, just tell them at least read this part, whatever we have discussed today, and try to understand it. Okay, otherwise they are not going to get anything that we are going to discuss in next 2-3 lectures. So just ask them to read this from the book and try to understand it. Okay, so we will solve this problem further in the next lecture.